All
Or
right, I'll mute myself when you do the recording because I'm
oh, we're recording
outside.
now.
Oh,
That's all right. Don't worry about it. So we can start with any questions you have. I just have so I can timestamp. So when I put this up, people will be like, "Oh, you can just click to a certain point." So it allows me to, anyone who watches this afterwards can be like, "Question 2 is talked about at this point." So awesome, Latano. So what questions do you have on the homework?
I actually didn't have any. I just was checking out and seeing what you were going to talk about. Really,
you're the first person here. Hopefully, some people come in with questions, or else don't worry. There's no questions. That's quite fine.
Okay.
Oh, getting a little bit of feedback.
All right.
Yeah, I'm hoping some other people were trying to get in here. I'm clicking around to my email right now. Okay, Michael said, I tried. Oh, no, wait. He thinks I'm talking about a password. He's getting, please enter the meeting password.
So, yeah, it asked me that.
And how'd you get around that? Why is it asking people for a password? Let me go to settings.
It told me just to like, I was on the app and then it said, if you have an invitation, just re-click the link.
It said what if you have a...
If you have an invitation, just re-click the link.
Okay. Yeah, maybe that's what it's saying on his. Like maybe it says if you have an invitation. Yeah. Let me see. All right, let me type that to him.
Oh, it said he joined.
Oh, he just joined now?
Yeah, it said Mike joined the meeting. It just told me that.
There we go. Did you just re-click the link? Because there's Mike's in here right now. I think he has his microphone off. So we're all just like hanging out. You can type to us, Mike, or you can, sounds like you have your mic off, Mike.
Okay. Can you hear me?
I can hear you, Mike, it sounds like.
Awesome.
Cool. Did you just retype, or did you, what I was sending you was someone's name who joined. They joined with that name, not that was the password.
Oh, okay.
It was like, yeah, because I was right about to reply to you. Did you just like re-click the link? Because that's what Latano did.
Yeah, that's what happened. I re-clicked the link, and like once I'd actually downloaded the application, like the first time I put the link through, it was like trying to do the app or download the application. And the second time I put through, it actually kind of like already had downloaded the application, so it just went right through.
Okay, cool. Yeah. I've been using it a little bit, and it's pretty good. Like if I screen share with you guys, like let me bring up like one of the assignments. I'll show you guys what it looks like. You guys can check it out. Because right now we don't have any questions. But if I go to screen share, let's see this work. Screen share, and now you guys can see my desktop, correct?
Mm-hmm.
Yes.
So in the video, and we got some answers right here. I got the solutions up, so anyone who's watching this will get it. These first few questions on the homework is not that hard. But on YouTube, I can put up a 1080 video of this. Hopefully I don't. Hopefully the things don't take up too much space because my drive is lacking in space, small solid-state drive. But if you guys have questions, we can start talking about them anytime now. Like I'm going to stop the share, but that's what it'll look like if you ask a question. I start showing you things. Like I can go into R and show you things or whatever.
Well, let me organize my little screen here so I got my homework up at the same time or whatever.
Cool.
Okay, yeah, so I had a question on the first homework on just 2F.
Okay, on the first homework we just turned in?
Oh, no, the second homework, I'm sorry.
Okay.
The one that was easy.
Okay. And just because they're easy doesn't mean that they're, that they're super duper easy.
Yeah.
Let me get the timestamp on this. I mean, I wouldn't say they're the easiest things in the world. Okay. So you'll see me look over at the timestamp for when we're talking about this because I'm like making notes for when I post them on YouTube. Although it's nice dropped it. Okay, so let's look at that one right here, 2F. I'm going to bring it up here for myself. Okay, homework 2F. So this is about the value of the discrepancy between all expected and observed counts turns out to be 1.017. Below, and so everyone can see what we're talking about here. I'm going to go to screen share. I just want to confirm, this is the question you're talking about right here, correct?
Yes, sir.
Good deal. I'm not a sir, I'm just Brian. The value of the discrepancy between all expected and observed accounts turns out to be 1.017. Below is the simulated sampling distribution of D for 5,000 samples with no association. Is the association between location and gender statistically significant? Why or why not? And this is a great conceptual question, because this is the idea of kind of what you'll be tested on. If you look at this right here, this is when we assume there's no association, we times the row by the columns to get the expected counts, take the difference between the observed and the expecteds, then we square that, and then we divide it by the expected. Observed minus expected, quantity squared, over expected, equals cell chi squared, which we're calling discrepancy. Now, to get this 1.017, we're adding up all the discrepancies. So what you have to think about here is this first part. This is for the matrix that we worked with in this problem. This is for our matrix, this very first part. So we get a discrepancy of 1.017. That doesn't mean anything until we put it in context. It's just 1.017. What does that mean? Now, here's the important part, is we're going to simulate fake distributions. And the fake distributions are under the assumption that there is no association between the two variables. So
yeah, that's what I kind of don't understand.
So here's what we're doing, is we have all these people right here where we have people where they sit in class and their gender. Now, let's say you were to just take everyone and put them in a bag. You just put everyone in a bag, and then you have a male come up and you draw where he's going to sit, and you have a female come up and draw where she's going to sit. Now, if you think about this, that's kind of the idea of no association. If they're drawing it randomly, wouldn't they just kind of be like randomly placed throughout the class?
Yeah.
And so what we get right here, let me hop over to, there's the stopwatch. So we'll go over to there. And we'll type mosaic plot no association. And we'll get a picture here on, hopefully nothing crazy comes up and I don't have to delete the video. This one shows an association right here, but we're going to expect to see something like this when it comes to male-female, because this shows really no association right here, where something like this does show an association and it's going off the screen. But the closer the bars are together, the less of an association there is. If the bars are super close, is there much discrepancy here?
No.
No. But when we have an association, like if this was it, or even this is one of my favorite ones right here, there's a lot of discrepancy. Now, if we were to do this randomly, what would it look like if we were to randomly start drawing these out? And let's say we had an American come up and draw a size of fry. I always say this is the size of a McDonald's fry. Would they be, is there going to be an association if an American draws it randomly out of a bag?
No, but there could possibly be a little bit, but.
Yes, and that's the thing is, by chance, we could see some sort of discrepancy, right?
Yeah.
So here's the important thing, is that when we do this randomly, we would expect to see things closer to this or closer to this more, things where the bars are kind of all even. This is kind of what we expect. That one doesn't have them super even, just kind of scrolling through to see mosaic plots that show little to no association. The more discrepancies, the higher the association. The closer the bars are together, the less an association. The association is based on the degree of discrepancy, where this one right here has a lot of discrepancy. So with this in mind, what this picture here represents is if we were to simulate 5,000 fake distributions. So we make 5,000 of these distributions just from the data, fake. Like these are 5,000 fake distributions. They don't exist. Does that make sense?
Yeah.
So we literally have to put everyone into a bag and draw them all out, and that's one time. And then we put everyone back into a bag, draw them all out, and we do that 5,000 times. And what do we observe from that 5,000 times? We observe the discrepancy right here. So like the discrepancies that were common to occur, what discrepancies were really common to occur? Like what values of discrepancies were common discrepancy values?
Oh, 1.
Oh yeah, 1's really common. Anything else really common?
2.
How about like 10?
Oh, no.
Not at all. 10 is a very odd discrepancy. So when we observe a discrepancy of 1.017, we observe something right in about here. If I were to put a line.
Ah, okay.
That's where we landed. And that's cool that that shows up like that, luckily. So what we want to understand here is the probability of our results or results more extreme due to random chance variation, given that there's no association. Due to random chance variation, I think I said association. Let me say it all in one sentence here. The probability of our results or results more extreme due to random chance variation, given that there is no association between these two variables. Here is what we would expect to see given that there's no association. Here is where our results landed. And now we want to see results more extreme, which is going to be everything there. And everything I've shaded in, basically I can't shade in really well underneath it. If I could, that's what I'm trying to shade. All the bars shaded in are our p-value. And if you look at that, that's probably like 80%. I think most of us can acknowledge that that's way more than 50%. We need to see something that would not happen due to chance, given that there's no association. So once again, I'll reiterate, this distribution right here is what we expect to see given that there is no association. We should see discrepancies like this. If we were to see something way out here, that's not likely to occur. If we see something in this area, anywhere in here, obviously, would be likely to occur given that there's no association. It's hard to tell exactly when, and if we had these numbers, because we can actually have R generate the numbers for us, but if we had the numbers, we could figure out what percent of numbers are higher than our number. But at this value, it's pretty evident that like 80%, it's a lot. And so, yeah, our results are very likely to occur given that there's no association.
So would this type of like graph happen every time you did this? I mean, would it look like this? Would the discrepancies look like this every time that you did this little 5,000 sample?
Interestingly enough, what this graph looks like, this distribution right here, if we go away from the theoretical sense, is actually based on a chi-squared with 2 degrees of freedom. So it's based on the idea of, let's go here to chi-square applet. You will see, and what we're doing is not based on a distribution. This kind of breaks away from what we're doing. If you look at the similarities between these, they look a little bit similar, but ours is more true to what we have. The chi-square does start to get a bump, and maybe more looks like a chi-square with 3 degrees of freedom. Try to remember if there's 3 or 4 places to sit in the classroom. Because that would, oh, there's 4 places to sit. Yeah. So actually, this is a chi-squared with 4 degrees of freedom, because I was like, it doesn't, do you see how the, like right here, the bump, and it starts to slope, it goes up 1 right here and starts to slope at 2?
Mm-hmm.
And then look at ours. Bump at 1, slope at 2. Does that look very similar?
Mm-hmm.
Yep. And so we're actually not basing it on the chi-squared distribution, but the chi-squared distribution we could base it on would look like it. And that's one of the big concepts that might be hard for some people in this class, because a few people were like, wait a minute, I've been using distributions for forever. Well, distributions are based on assumptions. And you're only as good, your p-value is only as good as you are to adhering to those assumptions. So if you take away the distribution and say, theoretically, according to mathematics, this is what we should see. So we're taking more of a mathematical simulation approach, which is based on no assumptions. It's only based on the idea that these are independent of each other, which is what we're testing out here. We're not saying, I know these are independent, but when we use a distribution, we're saying, this distribution works well, and I know that. We're not assuming anything. We're just testing to see if there's no association, and then the probability of what we see occurring given there's no association. So it's kind of, that's the good thing here is, yes, we basically have built a chi-squared with 3 degrees of freedom. Degrees of freedom on a chi-square are rows minus 1 times columns minus 1. And so as you see here on this, there is 2 by 4. That turns into a 1 by 3. 1 by 3 is 3. 1 times 3 is 3. And that's why I put in here 3 degrees of freedom. 2 times 4 turns to 1 times 3, which is 3 degrees of freedom. Just rows minus 1 times columns minus 1. But we're not using that, technically speaking. We're saying, let's simulate fake results. And they're not really fake. It's simulating results based on the assumption that there is no association between the two variables.
So if that discrepancy was 1, would that, I don't know if I'm asking the right question here, but if that discrepancy was 1 instead of 1.017, would that be like the same as just the cell chi-squared count? Or am I?
Um, well, the total discrepancy we're observing right here is all the cell chi-squared discrepancies added up. So if the value of the discrepancy of all the expected and observed counts is 1.017, and we can just call it 1 or something like that, that's if you were to obtain the discrepancy for this cell, this cell, this cell, this cell, like all these in here, all of these, all the data in here, let me highlight it more correctly. Can I do it? Maybe I can't. I'm just trying to highlight the data values and not highlight the numbers. I think if I do this, I can do it. Or I can't. Just these numbers from 10 to 62. These are the numbers we're checking for discrepancy, not the columns, the margins, I should say, the column margin and the row margins. Those are not what we're checking for discrepancy. We're comparing each one of these values to an expected count, which would be obtained by assuming they're independent. To obtain an expected count, we assume independence between the two variables, and then we compute what would happen, which right here, the expected count is going to be, it's going to be 107 times 329. You see I take row total. I think. Do what? I'm taking row total times column total over grand total. 107 times 329 over 579. Once again to see it. Row total times column total over grand total. And that gives me an expected count right there. I'm going to copy my expected count because now I'm going to do observed minus expected. Then I'm going to square it. And then I'm going to divide by the expected, which if you notice, that's a very, very small discrepancy right here. The discrepancy is 0.02. And so that's telling me that this didn't vary much from what I expected it to be. I really found what I expected. I mean, the cell chi-squared, or the discrepancy as we're calling it, is a measure of how odd your value is, how different it is from the observed, how different the observed and expected are. And so in this instance, what we saw here is basically what we expected. If I tell you I'm going to pay you $62 and I only pay you $60.80, are you really that mad? Probably not. And that's what we're looking at here. That's the idea of a discrepancy, is you expect $62, you get $60.79, and you're like, well, I don't know, now I can't go buy a Coke. No, big deal. But if the discrepancy was something like, oh, you expected $100 and I only paid you $60.80, then we take that value, we square it, and we divide. And if I tell you I'm going to pay you $100 and I only pay you $60, basically, are you happy? No. And if you notice, here's the standardized value of discrepancy now between that. It's 25. And if you scroll down here, had we seen something, and this is just one discrepancy, it's not all the discrepancies added up, because this distribution is all the discrepancies added up. Just one discrepancy that big, which would, like, if I tell you I'm going to give you $100 and I give you 60, you're like, hey, wait a minute, you know, that's not going to happen by chance. So with this in mind, we'd have landed way over here, which is something that shows us there's something going on here. But if it's not so odd, we land over here. And there's no, this one, visually, you wouldn't be able to come up with the exact point, but visually we can agree that, I would even say visually, I know that this is not odd, because odd means less than 5% chance, statistically speaking. And this looks more than 5% over here. At some point over here, I'm going to get a little bit iffy. I don't want to really make value judgments graphically on something like that. I'd say, what do you think? Do you think that's odd or not odd?
I'd say that's the borderline. I don't know.
It's almost the cutoff. It's almost, it's that one's a very hard one, and I wouldn't want to make visual guesses on it. I want to know how many observations we had above that and how many observations total, because then that would give me the p-value. The percentage of observations above this tell me the amount of time we see observations, or discrepancies rather, extreme, this extreme, or more extreme. So if I take the amount that occurred at that and above that, I get the p-value, which is the probability of our results or results more extreme due to random chance probability, given that there is no association. And the big thing, given that there is no association, is why we created this. This is what we see given that there is no association just due to random chance. So we've created it. We've created what we see given that there's no association due to random chance. Because randomly, could we get a big discrepancy randomly? Is it possible? Is it possible?
I'm having technical difficulties. My computer just locked up because I hadn't touched it in a while. Whoops.
Oh, no.
Okay, I'm back.
All right. Is it possible? Can you see what I'm showing on the screen?
Yeah, I got it.
Is it possible we could get a discrepancy that big due to random chance? Is it possible?
Yes.
Is it probable?
No.
That's exactly the point. So we would say that a discrepancy that big would not occur due to random chance. So I think there's an association because this was all built on the assumption of no association. So if we get a discrepancy that big, we're led to believe that we're wrong about there being no association. We can move on. If you have more questions on this, you can ask it, or we can move on to the next one.
No, we can go on. I mean, I think I get that now.
Cool. Which one do you want to ask on next? I'll take the timestamp, and I got my notebook so I can write down when we ask the questions. My pen go. Which one would you like to ask about now?
Okay, hold on a second.
What do you think of this Zoom meeting setting? Do you think it works pretty well, or?
Yeah, I like this. This is great, man.
No, I think so too. It's like the future. It's like, oh, here, we'll just explain homework like this.
I know. This is the reason I wanted to take you again, is because you actually utilize all this technology that I never see anybody else utilize. So.
Oh, thanks. No, I'm all about teaching better and faster. And yeah, you took 201 with me, right?
Yeah.
Yeah.
Okay, now I can't get out of your screen, though.
Okay, so I think if you hit escape, it'll get you out. Like if you are stuck in that screen, escape will get you out.
Okay, cool. So we lost the other guy, did we?
We did. We lost Latano. No. Oh, good. This isn't using up my hard drive so much.
Maybe I'd just like to look at the next one. Right?
Sure. Which question is the next one? Just
Oh no, I meant like the next actual homework.
Sure.
Oh Lord. Hold on.
So I was expecting like 50 people in here. You get like all these webcams all around. So like, I was expecting I've only had like 4 people in here at one time, but I think you can do like 100 or something. I don't know. 25 is the max, I think. So.
God, that seems crazy.
I know. This is what I want to do for like Stat 201 review sessions now. Like if we do one on Google, because then I can automatically go to like sharing the screen and I can put this right on YouTube. And I don't know, it's pretty impressive if you ask me.
Yeah, and the fact you can put it right on YouTube after you have the meeting, you're killing 2 birds with one stone. That's nice.
And I think the idea of time stamping it, because then I can just put in the time codes in. Like I put 410 is when you asked about question 2F, and I'll just put that in the video and I'll have like a link. It's just like all you do is click it and it'll go right to that question. And then if people are watching like the YouTube video and they'll be like, oh, I need help on this one, it'll say like click it, and you just click there and boom, you're on that question.
Yeah.
I don't know. Trying to teach better.
Yeah, you're doing a good job, man. I appreciate all it, like I said before. Okay.
Got my Mario mug. Mario.
Man, yeah, I should have used I had a Lord of the Rings one, but I didn't. It says My Precious on it.
we had a guy we called Schmeagle in college.
Oh, I'm guessing he wasn't too fond of that.
He kind of thought it was funny. He was an interesting guy. He was really, really skinny. He wore like the same thing every day, and I mean like every day for like as long as I knew him. And so he kind of walked around, like sulked around, like slowly.
He didn't crawl or anything, though, right?
I don't know. He was an interesting guy. He went back to his home country and went into the Army after college. Like I called his parents and like, oh, you want to talk to Jerry? And I was like, yeah. No, oh, he's in the Army. And I was like, what? I was like, you're in the Army? Like, yeah. I called them on Skype, so there was like this weird reverb and everything. And they're like, oh, he's in the Army. I was like, okay. I wonder if I still have his number somewhere. I hope he's doing right. He was a good guy. He was just interesting. So.
All right. How about question? Let's just go ahead and look at question 1 on homework 3.
All right. Question 1, homework 3. I'm pulling things up. I'll set the time code. Nose keeps itching. Everyone can watch me itch my nose. So, I like this stuff a lot. So let me take the time code on this. To homework 3, question 1, let's say 2:40, let's 24 minutes. Okay. Time coded it there, but I'm gonna put a little bit before. Okay, your internet connection's unstable. That's awesome. If all of a sudden I go away, you'll know why. Okay, so I'll start sharing with you here in a second. I'm getting everything pulled up as we speak. And the big thing for a lot of these right here is being able to use the all correlations command. And I've seen this is where some people are gonna, like, everything's gonna blow up in their face, which is really bad. That's never a good thing. Let me go ahead and start sharing. Screen share, desktop. Okay. So what you're mainly looking at, this all correlations command that Dr. Petrie wrote is a command that allows you to really just run a lot. It has in it simulations. It has in it graphical responses. So it's going to do simulations for you, graphics, and everything. Now, a lot of interesting stuff with this is, let me pull up our studio here. Oh, well, we'll talk about it. If you go to the library and look at the default for it, it has things in there like seed. And I think a lot of people should understand what the seed is. When you run computers, a seed, do you know what a seed is, Mike?
No.
Okay, good. A seed, and believe me, I've talked to people in my office, they didn't know what it was either, so no one really knows. But a seed is like, if I tell you to start counting at the number 10 and count for 10, what are you going to do?
10, 11 to 20.
Yep, there you go. And if I tell you just to count, and I tell you count to 10, what are you going to do?
1 to 10.
Exactly. And that's what people do by default. So by default, everyone who runs this will get the same output by using all correlations. But there's extra stuff in the code like seed, which we won't always use. But if you wanted to do it randomly from other people, you could tell the computer, oh, do this random seed. And you can tell it a number. And it's not like it's counting on that number, but it's using it to randomly generate the data. So it might have some algorithm it uses, like select this, then select this. But then the algorithm changes if you tell it a different number. So by default, everyone gets the same things. So when we look at the basic code, we'll switch over here to the answers. When we look at the basic code, we're not using all of that. You don't even need, if I remember correctly with this code, because I've done it a few times now, if you look at the code you specifically need, and you're just directly getting some answers right here, so boom, make sure you call in the regress class library, because if you don't call in the library command, none of these are going to make sense. But what you're looking at right here is you need to make sure to give it the variable you're looking at right here. So there's not too much to this if you look at the command. So we go through and we look at the output we're going to get for this right here. We want to predict response rate, what 5 variables are most strongly correlated. So this is just checking the correlation here between all of them by doing all correlations. So when we scroll down and look through the data right here, the highest correlation is with homeowner. And I want people to understand something right here, is that what is the second highest correlation?
The renting.
Yeah. And I hate to think people are going to say that that's the lowest. That's where Stat 201 comes into play. You know, renting is going to predict response rate, or, you know, this isn't R squared, because R squared would be 36%, because R squared is just correlation squared. But they both do really well. I do find it interesting that this p-value right here is somehow calculated, while the other ones basically just say 0. And this p-value, I hope everyone would know, is extremely tiny. That p-value, we could just call it 0. I find it weird that it's
286. Yeah.
You have no idea how many people in Stat 201 would tell me, nothing against anybody or people in our class, but I'll have people tell me that that p-value is like 4.4. Like, they'll write down 4.4 on the test. I'm like, no, it's 0. It's scientific notation. But I understand if you haven't seen it in a while, and then, you know, it gets a little bit confusing. The variable most correlated, trying to make that so that thing doesn't come up there. Don't look at everything yet. So we'll bring back up the homework, so we're not looking at all the answers right. The variable most correlated with the response rate is obviously that the fraction of households that own their home. Calculate R squared and interpret its value. Oh, this is excellent. I remember doing this one now, but I mean, if you look at it, it's a lead-in to the next one, because R squared is just R squared. And Petrie, his interpretations can be a little different than mine. I always like to use the idea of blank percent of the variation in Y is explained by the variation in X. So calculating R squared for this is just going to be squaring R. And R squared must always be between what and what? What must R squared always be between?
0 and 1.
Exactly. Unless we're talking about R squared hold out or R squared adjusted. Maybe R squared adjusted can go negative. But don't worry, those are concepts for a later day.
Okay.
I didn't say those things. But yeah, R squared, the general R squared that we use is percent of variation explained. You can't explain more than 100% of the variation. It's like points. If can you still see me in a corner? Like, do you see me or no?
Well, yeah, I see you. Yeah, I see you.
You can see me.
Yeah.
It's gonna be like way too tiny. Like if you think about points on a number line, we can put a line through that explains 100% of the variation. We can't. These are all points that would go directly on a line. We can't do something that explains more than 100%. There's only 100% of variation to explain. Now, interestingly enough, there is where we can go negative. Talk about that a later day. But your R squared that you'll use, whenever you say R squared, unless it has some sort of qualification to it, it can never go negative. My free meeting will end in 10 minutes.
Oh, no. I just got that too.
Yeah, we might just have to redo it. I think UT is supposed to give me unlimited access on this stuff. We might just have to restart the meeting. We'll get through this question, then maybe we'll restart, and I'll put the two videos together. So if we get knocked out, Mike, we'll restart it.
Okay.
It's like, oh no, you got to restart the meeting. Why does it? So I'll let you figure out what R squared is, interpret it with the sentence I gave. That's that. Is the association between homeowner, HH, and response rate statistically significant? Do you think it holds practical significance? Yeah, I mean, what do you think, Mike, on these? I'll let you answer. I don't know all the answers, but you go ahead and throw some answers on these.
I don't have the data pulled up.
Well, okay, so well, I'll pull up the data. We'll cheat here.
Give me the answer so I can tell you.
Do I?
Wait, but it was homeowner, or it was homeowner and renting?
Homeowner response rate. I'm
response.
pretty sure it was those two. I don't think we're jumping ship here. Homeowner response rate, yeah.
Okay, well, yeah, there's obviously some, I guess 64%, right?
Okay, so when I say statistically significant, anytime we say statistically significant, we're always talking about a what?
P-value?
That's exactly it. So what would you tell me about the probability of our results or results more extreme happening due to random chance, given that there's no correlation? The probability of that is what?
64%. No.
That's R.
I don't know what the probability was, but it doesn't seem like it would be high.
Look over here. The probability of our results or results more extreme happening due to random chance, given that there's no correlation, is basically
0.
Boom. So, and listen to what we said. The probability of us seeing this by random chance, given that there's no association, is basically 0. So what are you going to believe about this? That this occurred by random chance, given that there's no association, or what?
There has to be an association.
That it looks like there is some sort of, it looks like we have evidence of an association. I would say this is very strong evidence of an association, because this would not happen randomly, or I mean, the probability of this happening randomly, given that there's no association, is very unlikely. And that's totally p-values right there. Now when we talk about practical significance, if I tell you that there's a 64% correlation, does that sound practical to you?
Not really.
It's a bit of a judgment call. And you see it's right there. I was going to 0.6 times 0.6 is 36. Like the R squared for this one is very close to 36, because 0.6 times 0.6 is 36, and move the decimal, it's 0.36. This one, apparently, the answer is down there. It's 42%. So 42% of the variation in response rate is explained by homeowner. So 42% of the variation. I want you to think about this. If I tell you 42% of your next test score will be dependent on something, does that sound significant to you? Like, does that sound like something you should care about? If I say, yeah, 42% of the variation in your test score will depend on one thing. That sounds pretty significant, and it does. The practical and statistical significance comes down to a judgment call, and I think that can be hard for some people because it's just hard because it's like, is that? But at this point, I think this one's a little bit obvious. But
64% actually is really significant.
Yes, and the correlation of 64%, R squared of 42%, correlation squared, and so I think that one is obvious. Where the gray zone, it really would depend on what we were talking about a lot of times. So it's hard to say where exactly the gray zone is. A lot of times in these classes, we try to avoid things like giving you 8%. We want to make it obvious with like 1% of the variation is explained, or 70% of the, or I think 42 is still way high. In the real world, it's hard to find stuff that really does that well of explaining things. And considering that this is so statistically significant, I do believe it has, it's extremely statistically significant. And to say 42% of something is explained by something else sounds pretty good to me. You just have to think about it just in the like, as you work more with these things, it gets more evident. So it's kind of a work with it, and you start to see it more and more.
So that's what the R is just with the one variable in turn are associated with only one other variable.
R is going to be, we generally use R for just linear correlation. R is the Pearson correlation coefficient. And so R is like the density of clouds, the density of points in a cloud. So the more dense that is, the more it looks like a 1. If you notice here, my R equals 1. Let me write these things right here. This is kind of a brief visual description right here. The one, it might be hard to read, it says R equals 1. The other says R equals 0.7. It's kind of in reverse imagery. I can't write backwards. I wish I could. But the more densely clustered the points, the higher the correlation. Correlation is just, mathematically speaking, we get into math, but we just think about, it deals with the strength, direction, and form of a relationship. Because things can have an association, but still have no correlate, or like little to no correlation. To draw something that has an association but very low correlation, you just need to draw how you feel when you're eating Thanksgiving dinner. That's one of my favorite examples. If you think about eating Thanksgiving dinner, you start out feeling really great, or you start out really hungry, you start feeling great, and then you get too full and you feel horrible. So there's an association on how you feel while eating Thanksgiving dinner. You start to feel better and better while you eat, you reach a plateau, and then you crash after you eat too much.
But it's not linear.
Do what?
But it's not linear.
It's not linear. So linear correlation is what we get when we get the Pearson correlation coefficient. It's a linear correlation, which can be highly influenced by outliers. In class, we're going to talk about the Spearman-Rank correlation, because Spearman-Rank removes the influence of, helps us analyze nonlinear relationships better, and removes the impact of extreme outliers. So we'll talk about that a little bit. Let's keep going. More questions? What are you thinking?
Well, I don't know. I haven't really looked at homework 3 that much. So, is there anything that any pitfalls I should be aware of or anything?
No, I think it's pretty clear on the code. If you look at it, it has a lot of example code and what we need to talk about here and what we need to understand when you're looking at correlation. A lot of this is on correlation, what we've been talking about here. I want people to, be able to talk about these terms. And also, I think one thing that really helps is reading the book a little bit. You don't have to, free trial, 15 days left. That's Adobe Acrobat. You don't have to know the book inside and out. But I really think Dr. Petrie did an amazing job with the book because it walks you through these things in a very elementary way. So, but what we're trying to hit upon, I'm really going to try not to have something that like, oh, you have to read this in the book, and I'm not going to say it in class. But I think reading the book reinforces everything. But yeah.
Yeah, I was planning, to be honest, I haven't looked at the book yet. I bought it, but I was planning on kind of like just doing a whole big catch up today.
Oh, good.
And just like looking at all kind of whatever material I had to possibly look at and seeing what, was valuable to me or not, or what I was going to try and focus on studying. So yeah, I'm gonna check out the book after this probably.
I think it's a really good read. I mean that because unfortunately I have to realize I'm coming in from a master's level understanding of statistics, so maybe things click a little bit better in my brain when I read it. But none of it seemed too mathy or too absurd. Like it walked me through really well everything he wanted to show me, which was stuff I already knew, but just his method of teaching it and explaining it, I think made it clear. Like when he shows like mosaic plots with relationships, without, how we get the discrepancy values. I thought it really helps understanding. Awesome.
Cool.
Do you want me to end the meeting, or do you want to ask a few more questions, or like we can continue the meeting?
Well, I guess I'm done. Do you mind taking it off shared screen or whatever?
Sure. Here, let me do
no,
that.
I can press escape. You said I can press escape, right?
Yeah.
Oh, yeah. Hold on. Oh, yeah, I can do it. Never mind.
Good deal.
Okay, hold on.
Stop sharing too. Okay, we only got